so this is a joint work with Justin Ward, who's also here. Better? Okay, so I'll start by defining the problem so that we are all on the same page. So this is a problem. We're given a matroid M, an monotone submodular function f on the matroid. We want to find a basis of the matroid such that the value of the function applied to this set S is as large as possible. Now, throughout the talks today, people have assumed that everybody knows what a matroid is, and this might be the case. But if by any chance somebody doesn't know, then I'll define two special cases which will be particularly useful. Just so that nobody is lost. I need an assistant. So we'll have everybody can see. So we have a uniform matroid. That's the all subsets of the universe U of size R. So that's one simple example. So when optimizing over a uniform matroid, we want to select R elements from the universe U such that the value of the function is as large as possible. This is also known as a cardinality constraint. Okay, so this is one case. And the second case that we will consider is a partition matroid. So we have some partition of this universe into R sets. And we consider all subsets of the form x1 to xr, where xi is in ui. Okay, so we have this partition, and we want to pick one element from each part of the partition. Okay, now if we pick exactly one element out of each part of the partition, this is known as a base or a basis. And if we select at most one out of each, then this is known as an independent set. And so this is all you need to know, and might already know about matroids in this talk. Okay. So now lights out. Party begins. So what do we know about this problem? So let's start with the bad news. So this is a vast generalization of a classical NP-hard problem known as max cover. So it's NP-hard, so we can't solve it exactly. In case you're interested in actually solving it, then it's a bit hard. And even more than that, it's hard to approximate better than 1 minus 1 over e, which it's about 62.3%. Even in the simpler case of a uniform matroid. Now, in what sense is it hard to approximate? So actually, two different senses. So one, Uli is also here, prove that it's NP-hard. And for this, so for NP-hardness, you need a concrete problem that is given to you explicitly. Now, in this value oracle model, where the function is given to you as an oracle, then there's also a hardness result, which is actually simpler and earlier by Nemhauser, Fisher, and Woolsey, perhaps in a different order. And they proved, yeah, because they had a few papers together, so they chose a few different orders of their names. So say this is not alphabetical. So if you want to do better than 1 minus 1 over e, then you need to make exponentially many queries. So it's hard in that sense. Okay, so that's the bad part. Now the good part, what you can actually do. So for a uniform matroid, the problem is very simple. So all you can do is 1 minus 1 over e, and you can actually achieve this using the greedy algorithm. So what does the greedy algorithm do? So you pick the first element that for which the function is as large as possible. Then you pick another element so that now the new set is as large as possible. And you continue in this fashion until you get R elements. So R is the number of elements you need to choose, and it's also known as the rank. Forgot to mention. Okay, so this is what you can do for the uniform matroid. And now in the general case, even only for partition matroids, then the same algorithm, it only gives a 1/2 approximation. Okay, and this is not good enough for us. We want a bit better. So what you can do, work of Jan with a bunch of other people, you can do this very nice algorithm, which Sefi kind of described, called the continuous grid algorithm, which is kind of the different gradient descent, although some people don't like this description. And the thing about this algorithm, so although in the end you get an actual algorithm, the real algorithm runs in continuous time. So it's not combinatorial. Now, there are some combinatorial versions of this continuous grid algorithm, but somehow you hope to have a simple algorithm which is maybe only a bit more complicated than the grid algorithm. Okay, so this was the problem that we set out to solve. Can we find an optimal combinatorial algorithm? And is it going to be better in any kind of parameter? So we were able to find this combinatorial algorithm, but it turned out that it's not better with respect to any parameter we can think of. But it's still pretty interesting. Okay, so what does this algorithm look like? So we said grid, it doesn't work. Now what's the second algorithm you can think of? This is local search. So what's local search? You start with some solution, say the one that you get by running the greedy algorithm, and now you say, okay, so if I replace this point with that point, then the function increases. And then you replace another point with the fourth point, and it keeps increasing, and eventually you get stuck in a local optimum. Okay? Now, is this algorithm any better? So no, this is only a 1/2 approximation, even if you exchange several elements at a time. Now, of course, the more elements that you consider for exchanging at a time, then this algorithm gets slower and slower. And it turns out that if you want to get something strictly larger than a half, so larger than a half by a constant, then you need to consider exchanges where you exchange a linear number of elements. Okay, so this is not so good. This is not going to be a polynomial time algorithm. But what if, instead of trying to run this algorithm, you are pretending that you are trying to optimize a different function g? Okay, this is known as non-oblivious local search. So this is maybe a bit strange, but if you choose the correct function g, then this does give you a 1 - 1/e approximation for your original function f. Okay, so this is the algorithm, and to complete the description, I need to give you the function g. So there is the function g. When you can read the description, you'll hear much more about the function g throughout the talk. There's one thing about this algorithm. So there's one simple problem. You can't actually compute this function g. So it's some sort of weighted sum over of the value of the function f over all subsets of s, of which are exponentially many. Okay, so what you do instead is you sample. And that makes this algorithm randomized. Okay, and as we will see in the next talk, we really prefer deterministic algorithms. Okay, so now what I'm going to do in the rest of the talk, I'm going to explain the ideas of the analysis, but skip all the calculations. And then I'm going to explain to you where this function g comes from. Okay, so we start, this is for the experts. We start by a reduction from the general matroids to partition matroids. So there's this exercise that you can give in class, a lemma of duality. So if you have two bases of a matroid, then you can always number the elements so that if you remove Si from S and put in Oi instead, then you get something which is still a basis or an independent set. Now, in the partition matroid, that's pretty obvious because you take the ith element and replace it by some other ith element. But it turns out that you can also do it for a general matroid. Now, if for example, you wanted to do the same with O at the same time so that you can replace Oi with Si, then it's not necessarily the case. There are some matroids where you can't actually do it. So it's a bit constrained, but this is enough for us. So for our algorithm, really, the most general kind of matroid is a partition matroid. Okay, so what do you do now? So O is going to be sum up, yeah.
So basically you meant that this is a many-to-one mapping.
No, this is a bijection. This is a bijection. So
this is a matching.
Yeah, a matching, but it only works one way. It's like a directed matching. So you can replace elements from S with elements from O, but not the other way around.
What would be the other way around?
so that you can do this, and you can also do it on the other side. So at the same time. Yeah, that's called an SBO Matroid. Yeah, I think. And not every Matroid is. Yeah, so we let O be some optimal solution, and S be some local optimum. So what's a local optimum? It's a set that you can't improve by switching one element with another. That's a local optimum of G. So now what do we know? We know in particular that if you try to replace SI with OI, then this doesn't improve the value of the function G. Okay, that's what you know. And now you have this main lemma, which is this calculation. So first, if you do have this lemma, then this part here is going to be non-negative. And you get that f of s is at least 1 minus 1 over e times f of o. So e over e minus 1 is the reciprocal of 1 minus 1 over e.
So you said you reduced the problem to partition.
Sort of. Yeah. Yeah. So in the analysis, really, we never see full matroids. We look at the magnifying glass only locally, and it looks like a partition matroid. Now, how do you prove this lemma? So this is some kind of linear inequality. And so you write all the submodularity constraints, the monotonicity constraints, and you choose some non-negative linear combination, and you get this. So I'm not going to describe you this linear combination, but if the statement is true, then we know that it must be provable in this way. And I'm telling you that this statement is true. So there's a proof that looks like that. And indeed, the first proof did look like that. It was a big mess. And now we have a readable proof. But I don't think that's very important. So just take it for granted. So that's how you analyze the algorithm. Now the question arises, how on earth did we come up with this ridiculous looking function G, right? We didn't just, have an angel told it to us. So here's one way to find G. It's not exactly what we did, but it's kind of close. So we consider a general form, a general parameterization of functions G, which could be used in this context. So how do these functions look like? So the function G at a set S is going to be some linear combination of f at subsets of S. Okay, and the coefficients for symmetry reasons are only going to depend on the sizes of the two sets S and T. Okay, these are these coefficients C. And now we write this optimization problem. So we want to find the best coefficients. This is the maximum over C that maximize the approximation ratio. Now, what is the approximation ratio? So you have to take the minimum over all functions f. Minimum over what? Over all monotone submodular functions f. So of the ratio between f of s and f of o, or stated differently, f of o is 1, and you want to minimize f of s. And you also need that s is this local optimum. Okay, so if you could somehow solve this optimization problem, then you would find the optimal coefficients C, and the value of this program would be the optimal approximation ratio. Okay? Now, how do you solve this program? Any ideas? Justin?
I probably want to dualize the inside.
Yeah. Right. So you want to dualize the inside. So now you get a maximum from maximum. And it turns out that nothing bad happens, and you can collapse it to a single maximum, and you get a linear program, which you can then solve in a computer. And that's what we actually did. We solved it on the computer for small values of the rank until, I don't, like 15 or something. And then we generalized. So it's experimental mathematics. Okay, so that's one way to find G. I should also say that when you do this, you get a slightly better G, which gives you a slightly better approximation ratio, but sub-constant improvement. And now let's look at a different way of conceptualizing the function G that explains most of its properties. So first of all, I'm going to give you another formula for this function G. So we define fa of x to be the marginal of a with respect to x, or the other way around, depending on what you prefer. So it's by how much the function f increases when you add the element x to the set A. And now there's a different formula for the function G, for the marginals of the function G. So the marginals of the function g are some weighted combination of marginals of function f on the subsets of the input. Okay, and then again for the experts, so all of us are not supposed to know what the continuous relaxation is. So let's consider the function that maps b to the marginal of f of b with respect to x. And now we're going to plug in the constant vector p supported only on a. Okay, so that's this phi p, 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 p. And now we take this integral. So we choose p randomly. Or a different way of putting it, to compute the GA of x, what we do is we choose p randomly according to this probability distribution. And then we choose a random subset of a by picking each element with probability p. And now the expectation over all that is the value of the function g, of the marginal of the function g. Okay, so now that looks much more reasonable. Now it turns out that g is monotone and submodular as well. And it's also sort of more linear than the function f. So if you apply this process infinitely many times, I think you converge to a linear function. Okay, so this explains some of the properties of g, but now I'm going to explain how you can actually derive this formula for g, sort of. So again, we consider a general form of this function g, of the marginal of the function g. So it's going to be some linear combination of marginals of the function f on the subsets. And now we have these coefficients gamma that, again, for reasons of symmetry, they only depend on the sizes. Okay? And now it turns out that, well, if you want to guarantee that g is always monotone, whenever you plug in a monotone f, then these coefficients have to be non-negative. Okay, so hopefully this is easy to see. So certainly if the coefficients are non-negative and f is monotone, then all the marginals are non-negative, and so the marginals of g are non-negative, and so the function g is monotone. And the other way around also should be similar. Now, a slightly more difficult, but still a very simple exercise. So if you want g to be submodular, that what needs to happen is that there needs to be some distribution gamma on subsets on the universe and some positive constant c, such that to calculate the marginal at the points a and x. So you draw this set T from the distribution gamma, and now you compute the intersection with A, and you take expectation over that, and you optionally multiply by C if you want. It's just a scaling factor. So we will choose C equals 1. Okay, so this maybe doesn't look like it, but it's a pretty simple calculation. Okay, so this already explains why G has this form that you pick a random set somehow. But now for the actual expression, we have this nice theorem in probability theory called De Finetti's theorem. And it states that in this case, it must be the case that the way that you generate this gamma is you first choose this random P, random probability P, from some distribution capital P. And then you choose this subset by picking each element with probability P. And all you need for this theorem to work is, well, first, symmetry, that everything is symmetrical. And second, you need the universe to be infinite. Okay, so if it's not infinite, you can actually do a bit better, as I said before. So just, we're taking the limiting case, and in the limit, then this is actually correct. Okay, so to finish the description of this function g, I need to tell you how we got the particular distribution capital P. Okay, so I can't really do that without getting into the proof, but I'll give you some hints. So when you do the proof, then, so if you recall, there's this main lemma that states that some constant times f of s is at least f of o plus some expression involving g. Then, so if you want all the other terms that you don't see there to actually cancel, then it turns out that what you need is that this cumulative distribution function pi of p satisfies the differential equation of pi prime equals pi. Okay, that's what it turns out to be. So then you can solve for pi prime.
You mean the pi prime is a derivative of?
Yeah, sorry, the derivative of pi is itself.
Using p.
Yeah, respective p. Yeah, that's the only variable here. And then you can get the entire form of this distribution pi. And it also turns out that the approximation ratio of the algorithm is 1 over the derivative of pi at the point 1. Okay, and this is 1 minus 1 over e. So in the continuous greedy algorithm, you got the approximation ratio by solving some differential equation, which was different than this one. And here again, you have some differential equation, and yeah. Okay, so I guess this is all I have to say about the original algorithm. So let me just say that there are some thoughts whether perhaps there is some connection between this algorithm and the continuous greedy algorithm. So why do we have these thoughts? So if you look at the expression here, so it's sort of like doing the continuous greedy algorithm, but at all times at once, where we weight the different times with respect to this probability distribution. And this is even more so if you consider the combinatorial version of the continuous greedy algorithm, which I haven't described. So this is kind of very strange connection, but maybe there is a better connection that will help us see what's really going on. So again, to help us see what's really going on, then we'll consider a special case, a case of coverage functions. So a function is a coverage function if you have this coverage setting that this function f represents. So this is the setup. We have some universe U of elements, and each element has some non-negative weight, or if you prefer, it's strictly positive. And again, you have this matroid on subsets of U. So each point in the matroid now is a subset of U. And each basis of the matroid is a collection of subsets of U. So it's very confusing. And now what's the function f? So you give it these points in the matroid, which are subsets of U. Now you take all the elements in U, all the elements in these subsets, and you sum all the weights, and that's the value of the function f. Yeah, this is a coverage function. Now, alternatively, a coverage function is a function that satisfies derivative constraints of all orders. So monotonicity is like the first derivative is non-negative, submodularity, the second one is non-positive. And the coverage function also has the third one, the fifth one non-negative, the fourth and the sixth non-positive, and so on. This is equivalent. Okay, so now if you do the calculation, then you get that this function g that we like has the following very nice form. So on input S1 to SR, you take all the elements in the universe, and for each one, you count how many times it appears in the input. So how many sets of the sets in the input contain it. And now you boost the weight of this element by some sequence of coefficients alpha. Okay, that will satisfy, it's going to satisfy alpha of 0 equals 0. Now what is this sequence of coefficients? So it has lots of forms. This is one form, which now should look familiar. You can also solve this integral and get this double sum if you prefer. You can also get a recurrence, which I'm not going to write. Something very curious is this grows like log k. For some reason we don't really understand. Here are the first few values. Okay, so this algorithm is actually deterministic, because here there is an explicit form of the function g that you can actually calculate with. Okay, so I'll end with a few open questions. So very quickly, one, there's an open problem for a matroid intersection. The continuous greedy doesn't seem to work. This also doesn't seem to work, but maybe. Niv will talk about deterministic algorithms. So can we use this or any other algorithm to get a deterministic algorithm for monotone submodular maximization over a matroid? And finally, so this is one use of this not so popular method, non-oblivious local search. Maybe there are others. And now that you have seen this method at work, then maybe you can come up with them. So we've tried and failed, but maybe you're smarter than us. Okay, so that's all I had to say. I'd say quadratic, but that's just a guess. It's the same as in continuous greedy.
Roughly the same.
Yeah.
Does it depend on the range of the values of f?
No, because the function is monotone, then, well, it can't behave too wildly. So, and the value you're trying to estimate is always, yeah. Yeah.
So either for this algorithm, for the continuous greedy, you really need to sample f on sets that are not independent, right? So
No, for this algorithm, actually, you don't need to.
you don't need to
No.
sample to compute this G.
No.
This is interesting.
So here's the definition of G. It's only a subset of S, and S is always the basis.
Right, because for the continuous greedy, you do need to sample outside.
So I think the combinatorial version of the continuous greedy algorithm was an appendix to one of the paper. Also, I think doesn't need to.
You could have an oracle that only answer queries inside the matrix.
Yeah.
Well, for the local search swaps, you need to check all the points, right? But not all sets.
No, but it's still a basis. Yeah, you need to consider all possible exchanges.
It's
Yeah.
not like you're restricted to a small subset. You still have to touch everything.
Well, but all the sets are independent still. Now it might be the case that it's better to do the exchange that results in the maximum increase, but we couldn't prove that it actually improves the time of conversions. So, but I think people often do it in practice.
Just to confirm that the whole analysis works for general stuff like
Yeah.
not just but for all Matroid constraints.
Yeah. Yeah.
So it seems that you have a nice conceptual way. It's quite new, right? More conceptual way of deriving the function g.
Yeah.
So if you try to follow that route for two Matroids, you get
So
something,
if you do the same sort of exchanges, you can't get a different function because this is the only function which gives the 1 minus 1 over E approximation, the unique function, up to scalar multiple. So you'll need to consider more complicated exchanges.